What's up, Anthony? Yeah. Yeah, and I realize we're sort of like running just a little bit behind schedule. Sorry about that. So I'll give people maybe like, 12-minute reminder, like, hey, time is starting to it's starting to end. So yeah, we'll just try to keep it at 15 minutes from now on for the rest. I mean, I know we started late and whatnot, so awesome. Thank you.
Yeah. Okay, I am sorry in advance. I'm going to be pushing 15. I want to show something.
It's probably fine at this point. Yeah. Whatever.
I'll try to keep it moving. But so yeah, so I'll be talking a bit about communication complexity. Admittedly, I'm certainly not an expert in the field. This is something I've started looking at recently, but I think is really cool, and I wanted to just kind of share one nice result from the field.
Yes, we can't see your screen. It just says you started screen sharing.
Okay.
Yeah, maybe try again. See if.
Yeah. Okay. Thank you for letting me know. So it says on my end your screen sharing is paused, and there's a resume share button, but when I click it, nothing happens. Okay, let me try. Maybe if I share it in not presentation mode, we can just do it this way. See. Okay, so you can see it now, right?
Yeah.
And if
you should be able to do a presenter view and have things work. At least that's how it worked with me.
Do this.
Yep.
We're good.
Yeah.
Okay. Fantastic. Okay. Can I extend? Okay. Yeah. So like I said, I'll be talking about communication complexity, and in particular, I just want to show one nice result from it. So I don't know how to use presenter view. Okay. All right. We'll make this work. Okay. So just to recall, like what the main goal of complexity in general is, right? In TCS, we're interested in how much of some resource we need to solve a task, right? And so the resources that we conventionally study are things like, sorry, neighbors are crazy. Are things like time, space, even stuff like randomness. But I'm here to tell you about one more that's maybe less talked about of communication. All right, so let's look at this closer. This slide's going to be several definitions. I will present examples after this, so don't worry too much if this is all in the abstract. But our goal is, right, if we have a function whose inputs are distributed among several people, right, how much communication do we need between these people to evaluate the function? All right, simple enough. And okay, so how do we analyze this? The first thing we need to do is look at protocols. So protocols are how this group of people gets together before they're all assigned some part of the input, and they say, okay, here's how we're gonna combine our input or talk to each other to solve this function, right? Like, so okay, I'm gonna first send you this bit if this is true, and the other bit if this is true, and then you're gonna send me this, I'm gonna send you this, et cetera, right? So they all agree on how this is gonna work. And we're gonna measure kind of the communication complexity by the number of bits required to communicate for the worst input, right? So remember, we're trying to evaluate a function. So there's a lot of different possible inputs people could receive. And we're going to look at the number of bits required in the worst case is the communication complexity of a particular protocol. All right. But remember, we're interested in the communication complexity of a function, not of a protocol. So we'll define the communication complexity of a function as the least communication complexity for any protocol. So this is kind of like a min-max type of thing here. Again, I'll show examples. Hopefully this at least sort of makes sense, but I'll give a brief pause for questions. Okay. So why should we care about this, right? I will admit off the bat, I think this is maybe a less natural question to study than traditional questions in complexity. Like I don't think this is as natural as trying to figure out how much time or space a problem takes up. But it turns out that this is much more useful than it would at first seem in terms of applications. You can prove things about data structures, circuit complexity, streaming algorithms, Turing machines, even stuff in just like pure mathematics like combinatorics can come from this framework. And on the flip side, it uses a lot of very interesting tools. Everything from linear algebra to information theory, et cetera, et cetera. As a very slight tangent and piece of advice to undergrads looking to do research, take this for what you will, as like from a first-year grad student. But I think a lot of people will overly emphasize when you're trying to determine what problems to work at, like the implications of solving these problems. But I will argue it is at least close to as important to be aware of what style of techniques you probably need to prove something like this, right? Like there are a lot of results that I care about that I hate working with these certain techniques, and I'm not going to make any progress, right, if I'm miserable doing this. So just I would keep that in the back of your mind. This is not to say like this is, if you don't know a technique, that's different. You should learn it. But if you know it and you know you don't like working with it, then that should be considered. All right. Okay, so I promised an example. Here's a very simple one. We have our good friends Alice and Bob. They both possess some bit string, right? And they want to decide if these two bit strings are equal. Now, there's an easy thing they could do is Alice could send Bob her 5 bits, right? Bob can compare them since now he has both bits. And he can send back a 0 or 1 telling Alice if they're equal, right? Straightforward enough. And this will be 6 bits. Can we do something better? Well, no, it turns out for equality, the best thing you can do is just someone sends someone else their bits and then the other one tells them their answer. Okay, maybe that's interesting, maybe not. But let me tell you about what I think is an even cooler protocol. So now we're going to introduce Eve. She will no longer be malicious. Now she's our friend. And we want to determine whether or not all of our numbers, so in this case, we have numbers, I'll say natural numbers, instead of bit strings. We'll determine whether all our natural numbers add up to some fixed value, 1,000 or something, okay? So how do we do this? And before we do this, I'll mention, okay, it turns out this generalization from 2 players to 3 players is not as interesting as other models. It turns out what we can do and make this more interesting and actually have more applications is to, instead of thinking of everybody having their own input and you not being able to see anyone else's, instead we're going to think about our inputs as being on our forehead, like heads up, if you've ever played the phone game or something like this. So you can see everyone's input but your own. All right. And again, I won't really talk on why this is a useful thing to do or gives more applications, but it does. So again, so like in this case, Alice can see Eve's and Bob's input, but not her. And we wanted them to come up with some way to communicate to see if when they add up all their numbers, it equals n. Okay. Clearly, we can do something similar to what we did last time. We can have, say, Bob tell Alice what's on her forehead, and she can figure this out and tell everyone. I guess it's worth mentioning that communication in this setting, we think of like happening on a blackboard. So people aren't speaking like from one to the other, they're writing it up front so everyone can see all communication. So Bob can tell Alice what's on her forehead, and this will take about log n bits. And we're very short on time, so I'm not going to give you time to think about this, but I will suggest if you do, it's very unclear how you would do better than this. And in part, it seems like this is what you kind of have to do, but I'm going to show you a protocol that is substantially better. And to do this, we need to take a trip into Ramsey theory, which is an area close to my heart, and look at something called combinatorial corners. Okay, what is this? We're going to look at subsets of pairs of numbers, right? Each number comes from 1 to n of the form AB, A plus B, A, B. You'll see in a second with the picture, but it looks like a corner when you kind of draw it. And there's a very nice theorem that, again, I'm not going to prove, but it's not terribly hard to prove, that if you give me some n, so we have like some grid, then I can color all the points with not like too many colors, such that there's no monochromatic corner. There's no corner all of the same color, right? So let me give some pretty visuals here, right? So if this is our grid, all right, this is what a corner would look like, in particular a monochromatic corner, right? Each of these points is the same color. A corner is going to be something where they're like spaced the same vertically and horizontally. And this theorem promises that there's some way to color the grid where there's no corner that's monochromatic, assuming I did this right. So, okay, this I guess is interesting, but how do we connect this back to our problem? Which again, I'll just remind you very briefly. Right, our goal is to figure out if we have our number on our forehead and can see everyone else's, do all our numbers add up to a fixed number, and we call that n. Okay. So here's the protocol. This is going to be like the last slide. Here's what we're going to do. Beforehand, so like before we're all assigned our inputs, right? We're agreeing on a protocol. Part of agreeing on the protocol is going to be agreeing on some coloring of our n by n grid without some monochromatic color corner. Okay, and we know that this coloring has to exist by the theorem I just told you about. Okay. Next, what we're going to do is, well, okay, just for the sake of naming things, Alice's input will be X, Bob's will be Y, Eve's will be Z. And the first thing they're going to do is each look and make sure there's a possible value they can take to satisfy the equation. So, okay, what does this mean? Let's say we want to try to figure out if all our numbers add up to 1,000. All right. If I'm looking at all the other players and I see that their numbers already add up to something more than 1,000, right? 2,000, for example. There's no number on my head that can satisfy that I can add to 2,000 to get 1,000 if we're just dealing with natural numbers, right? There's nothing I can do. I already know that this function is going to evaluate to 0. So we all check, like do like a sanity check, right? Like, is this even possible? If it's not, we write a 0 on the board or something and we're done, okay? So we can assume that this does not happen. There's some value that we can take to satisfy this. And what are we going to do? Say I'm Alice. I will figure out what this value needs to be for my forehead, such that all the numbers I see plus what's on my forehead equals what we want, equals n. Okay. And now I'm going to do something a little weird. I'm going to output the color of the point at index x prime, where again, x is what I calculated I need to have on my forehead, and y. Why? You'll see why we're doing this in a second, but bear with me. Bob is going to do the same thing with y prime and output x comma y prime. And finally, Eve is going to output the color of xy. Okay, and I claim from this we're done. Why? X plus y plus z, right? Their inputs equal n if and only if they all say the same color. Why is that? Okay, if x plus y plus z equals n, then this x prime and this y prime that they calculate of what they need to have on their forehead is actually x, and this is actually y. So in other words, Alice outputted the color of xy, Bob outputted the color of xy, Eve outputted the color of xy. These are the same point, so of course it's going to be the same color. Okay, so that's fine. What about if their inputs do not sum to n? All right. In this case, I claim that we, if their inputs do not sum to n, and they all output the same color, what does this tell us? This gives us a monochromatic corner. all right? But we promised ourselves, or we were promised beforehand that this coloring has no monochromatic corner, right? So this is a contradiction. This can't happen. And this is, okay, formalizing this a little bit. Again, I mean, this is essentially what I said. So there's a question in the chat. Yep, I know, I'm so sorry. Okay. Yeah, so this is this. So, okay, let's look at the total bits exchanged. We output 3 colorings. This will take about square root of log n bits. If we were to just give someone the input on their forehead, that's log n bits. So this is a dramatically more efficient protocol. And again, I mean, this is not an obvious thing you would come up with, right? So I don't know, I think this is very beautiful. And I think this, gives 2 takeaways. 1, communication complexity is very cool and very interesting. And 2, lower bounds are crazy hard, right? Like there are a lot of nice results that come out of proving lower bounds in communication complexity. But right, the problem with lower bounds is you have to somehow come up with rigorous ways to prove that you can't do stuff like what we just did, right? These like using kind of a weird result from like Ramsey theory or other weird results from other fields, right? You have to be able to rule all of these out. And this is quite challenging. All right, so credit where credit is due. I kind of stole a lot of the presentation format from Bill Sarch over at University of Maryland. And the material itself is from a nice paper by Chandra First and Lipton. So let me stop here for like speed run questions, so I don't take up any more of anyone else's time. But yeah.
Yeah, maybe we can drop some questions in the chat if we have
Yeah.
any. Thank you, Anthony. Those were really nice slides and a really nice problem to go over. Awesome. Yeah, I think next is Natalie. Yeah,
Cool, I can share my screen. Sorry,
Yeah.
finish whatever you're gonna say.
No, yeah, feel free to get started. Thank you for.
Okay. Yeah, here. So I tried to make a Jamboard and I want to share it. So let's see if let me try to do this in like minimal way. Okay, are you all seeing this?
Yeah.
Okay, cool. So I'm just gonna present this Jamboard myself to all of you as if it is PowerPoint. Yes. Okay. Hi, everyone. I'm Natalie. I'm one of the TAs. I'm a first-year grad student at the University of Pennsylvania, and I like game theory, and I think you should too. And today I'm going to talk a little bit about a couple different notions of equilibria. And this may be a notion that's familiar to you, it might not, but either way, I bet there's some definition of equilibria I'm going to tell you which you haven't heard about. Okay, so first, we're talking about game theory. So what is a game? Okay, so you know, depending on whether you formally study game theory in the context of theoretical computer science, or whether you just have played games, you might have a different notion as to what a game is. But the general definition of a game that you have when you're like playing cards or anything, it's not super different from what I mean by a game. It's got all the same elements. You gotta have players, more than one. You gotta have the players making decisions, and then there has to be some consequence to these decisions. That's the payoffs. So one example of a game that you might have all played is rock, paper, scissors, right? So you have 2 players, right? Then they have decisions. And this is a simultaneous game. They're both going to choose a decision. They're going to make it. It's going to happen at the same time. And there's going to be a payoffs. You can write this as a matrix, right? If every player has like a rock, paper, and scissors moves, you can sort of see, you can imagine that maybe if you win, you get a numerical payoff of 1, lose, -1, and tie 0. So we can populate a payoff matrix. There we go. That would kind of reflect this. See here, rock and rock. This would, I don't even need to do this because you can see my mouse, but hopefully it's apparent that while maybe you're not convinced that I can represent all games you could possibly think of in this matrix, at least you can see how rock, paper, scissors can be represented as a payoff matrix. Okay, well, when we think about games this way, we can also think about the notion of a Nash equilibria, which is just defined as a pair of strategies. Right now I'm just focusing on 2-player games for the rest of this talk, such that if either player looks at this pair of strategies, they look at what the other person is doing, they look at what they're doing, they're not incentivized to change what they're doing. So let's think about how that works with respect to this rock, paper, scissors game. So it seems strange because how could this be possible? So say that one of them saying, say rock, the other one saying scissors. Well, this first person is gonna be like, well, wait, like, I don't want to lose. So I'm gonna change to paper. And this person's gonna say, well, I don't want to lose either. So I'm gonna switch to scissors, right? And so on and so forth. So it feels like this is an impossibility. But what I haven't told you is that you're not just having to declare what I call pure strategies. You can also declare mixed strategies. So what if instead of actually saying, oh, I'm definitely playing scissors, this first person had said, well, my strategy is this. I'm going to flip a 3-sided coin, and with 30%, with a 1/3 probability, I'll play scissors, 1/3 paper, 1/3 rock. And then the other person says, okay, that's my strategy too. So at this point, this is an equilibrium with these two mixed strategies, because neither player, so if I'm one of the players and I'm playing a strategy where I'm doing 1/3, 1/3, 1/3, and I look at the other person, it turns out there's just no way for me to change what I'm doing, such that it's going to give me a higher payoff in expectation, right? This is all an expectation because we have this randomness here. And this kind of intuitively makes sense, right? Like rock, paper, scissors, it's a symmetric game. It's hard to imagine how one could do much better than just playing randomly. And it kind of makes sense that if both players are playing randomly, this feels like a stable situation. Nash equilibria are this sort of a fundamental notion in game theory that is hoping to capture, something about the steady state of games. And one of the seminal results in game theory was when Nash proved that they always exist. And that's great. So every game has at least one, maybe not pure, but perhaps a mixed Nash equilibrium, right? But they are, so for example, this game, this one has a mixed one, not a pure one. They are, though, very, very hard to compute. This is in the class PPAD complete. It's just like we think, we don't know that anything's hard really, but we think this is hard. I say here also, there's multiple payoff outcomes. I'll talk a little bit more what that means later, because I want you to understand that this is a very fundamental notion of equilibrium, but it's not the only one. And I want to open our mind to some other notions as well. So I'll do that by introducing this other game. I'm going to call this the traffic game. I hope you appreciate my artwork. So here you have two cars that are driving towards an intersection, going fast, and they have to sort of make split-second decision. Am I going to stop or am I going to keep driving through? So we can imagine this as another simultaneous 2-player game with 2 moves for each player now, not 3. And one can imagine what might happen, right? If both players stop, this is kind of a pain because now they have to figure out who's going to go after this. So it's kind of awkward, but everyone will be fine probably. If one player goes through, the other one stops. It's pretty good for the player that goes through. They're still driving. The one that stops is kind of annoying. Same other way around. And if they both drive through, they might have a fatal crash. So this would be enormously bad. We can think about this as well in a payoff matrix. So here's how I decided to represent it, right? So where the red car is making these decisions up here between drive and stop, and the blue car is making these ones between drive and stop. Okay, so, and as you can see, I've decided both players are driving, they're both getting a payoff of -100, which is just sort of a different scale than if the other, if they, one player drives to get a small advantage. So hopefully this kind of makes sense as why this would be the sort of payoff matrix one might expect here. Where here I'm saying the first payoff is for the blue and the second one's for the red. Okay, so it turns out that let's think about how we would think about Nash equilibrium in this case. Well, it turns out there's exactly 3. One of them is when player 1, or say the red car drives and the blue car stops, right? So the move stop drive pair, right? Because you can think from either person's perspective at this point, if I know, if I see that I'm stopping and you're driving, right? I'm not going to want to drive because that'll be disastrous for me. I'll have a -100. And if I'm driving and I know you're stopping, well, that's great. I'm getting the best payoff I could possibly get of +1. So this is good for me. Same vice versa. And there is a third equilibrium, which is a mixed equilibrium, which involves both players not driving, like you can see here, with probability about 3%, or I guess about 4% driving and the rest of the time stopping. And basically this very small probability of driving kind of balances out the terrible risk that you would get from actually colliding with a person with the small payoff you get from trying. Okay, so let's think about what this means in terms of we had our problem, we found the Nash equilibria. Like, what does this mean? Like, and I want to argue that like maybe this isn't fully capturing the kinds of things we want to think about in the situation. Okay, so one of these equilibrium is saying one person's always stopping, the other one's always driving. One of them is the other way around. So these don't feel very fair. And the last one just feels stupid, right? So it's like the players are just like sort of like winging it. They're just like sending it like, all right, maybe sometimes I'm just gonna like slam on the gas and like hope the other person doesn't, right? This feels like a tremendously inefficient and bad idea. And in particular, like what's gonna happen here? Well, in the first one and the second one, the payoff for one of the people is +1, the other was -1. For this third mixed one, both their payoffs are like -2.9 or something. Like this is not a good situation. Because they're both stopping most of the time, and then sometimes they're crashing into each other. So is there maybe something more we can say? It feels like there might be, if we consider sort of like other things, a slightly different setting and have some more assumptions about what we can allow in our equilibria, maybe we could do better. And I want to introduce the notion of shared randomness in order to think about a different notion of equilibria called correlated equilibrium. So when we think about a correlated equilibrium, we're no longer just thinking about a particular pair of moves. We're now thinking about a distribution of strategy pairs. And something is that's a distribution of strategy pairs is a correlated equilibrium if we had two players in this case, I drew a strategy pair from this distribution, and I just told each of the people their side of the pair, but they knew the distribution. Would they be, if they would not be incentivized to deviate from playing that recommended strategy, then this is a correlated equilibria. And so let's think of some examples of this. So first of all, by the way, this also always exists, right? And it's actually easier to find in general. Like I won't get into the details of the complexity classes, but like this is generally an easier problem finding one of these. So how might we reason about how this game will work with correlated equilibria? Let's see if I can actually do some drawing here. So let me propose one correlated equilibria. One is, I'm going to draw from the distribution with probability 1/3. I'm going to draw, this is hard, stop. Okay, this is maybe not the most beautiful writing. My computer's like being very laggy, but with one probability 1/3, D for drive. Wow, okay, we're typing this. 1/3, stop, 1/3, stop, drive, 1/3, drive, stop. Okay, this is one example of a correlated equilibria. Okay, that'll have to be enough erasing for now. So let's think briefly about why that's the case. So say that I drew a pair and the pair told one of the players to drive. Well, this player is going to look at all of the strategy pairs where they were told to drive, and it's just this one, right? So without loss of generality, I'm thinking about player one here. So they actually know for sure that the other player is stopping. And in that case, it makes sense for them to follow it and drive. On the other hand, say they were told to stop. If they were told to stop, what do they know? They know that the other person is driving half the time, right? Because they know they're in this world now. And if the other person is driving half the time, you can just sort of work out the math and see if it's not worth them driving. So they're going to stop. That makes us a correlated equilibria. But actually, maybe a better correlated equilibria for this game is a more simple one, where we're just going to be more efficient here. And we're going to do a half chance stopping and driving, a half chance driving and stopping, right? So we're just sort of saying what's happening here is, yeah, so here's, there's like a lot of correlated equilibria. In this case, it's like a convex set, but this is a nice example of one. And this is sort of like adding a stoplight, right? We've added, like, there's a reason it's called a correlated equilibria. They're using the shared randomness to basically say, okay, like let's, instead of just sort of either having one of us always be the one that loses, or having sort of like like having to guess what the other person's doing in some way to get a mixed equilibrium that kind of hurts everyone. What if we have some sort of shared randomness that allows us to to coordinate and have both sort of a notion of fairness and a notion of optimality. So that's kind of nice. And in the last couple minutes, I'm going to introduce another notion of equilibria, which is called Stackelberg equilibria, because something else that you might ask is, well, it's kind of seems strange that we are always assuming that players are moving simultaneously. That's not really the way that things always work in real life. What if one player could say what they were doing before the other player? How can we reason about these situations? And so this is a setting called Stackelberg games. One player is the Stackelberg leader. Again, these all extend to more than 2 players, but we're just focusing on 2 players now. The other player is going to be the follower. And the leader gets to commit to a strategy, right? So they're going to get to say, hey, by the way, I'm doing this and I'm committing. And so I'm actually not going to get to change it. I'm like putting in my moves, they're in. And I'm going to, and I get to assume, because we're in a rational setting, that the follower is going to see that information and they're going to respond to maximize their payoff condition on this commitment. And something that's kind of interesting, because it feels like, well, you're kind of giving away a secret, is that it never hurts to be a leader. And in many cases it helps. And I'm not going to go through in detail why that's the case, but here's an example payoff matrix on this side where the leader is the role player, and they actually do significantly better if they are in the Stackelberg as a Stackelberg leader than they do in any Nash equilibrium. And in particular, the Stackelberg equilibria is the commitment strategy that the leader can employ given this setup, which gives them the highest expected payoff. And Stackelberg equilibria can be computed at least in 2-player games, just sort of with a polynomial number of linear programs. I guess linear in the number of strategies. So it's a much easier thing to do than finding Nash equilibrium. And there's also something nice about the fact that while there might be a couple different things that the leader can do to get this, it's going to be the same value, right? The Stackelberg equilibria is defined as the strategy that gets them the highest payoff. So the Stackelberg value for any game is very well defined. There's exactly one Stackelberg value for any game. Now, I don't really know how to whether this actually is a good example for the motivating example of driving, because I think correlated equilibrium makes a lot more sense. But if we were to try to imagine what's happening here, it might be something like this. One of the players is I cut my brakes. So obviously at this point, this other person's knows for sure that they're can't stop even if they wanted to. And so this red player, they might as well stop. Yeah, so I just summarizing various notions of equilibria for this game. And I'll stop there because it looks like I'm at 15 minutes. Thanks for listening.
Yeah, thank you so much, Natalie. That was great. Yeah, and also I know you're in the social committee, so you can give us the permission to be a little bit late, right?
Oh yeah, we actually don't have a game today, so there's permission to be very late. It feels like in general people have been kind of burned out by the end of the day, but we will have something for tomorrow.
Okay,
but
great.
Yes, so you have lots of permission to be late, infinitely late.
Yeah. Okay. So now that we have the permission, I will. I refer to Chunk to present his own work. Interests.
Okay. Okay. Can everyone see my slides?
Yes.
All right. So I'm going to talk about proof systems as they're used in practice. And this is in some ways a continuation of Yao's lecture from yesterday. So I'm going to be just giving a very high level overview. And then at the end, maybe I'll mention for 10 seconds, where my current work lies within this breaks. This very various research directions that this field is having right now. Okay. So let's start with the motivation. Why do we want to apply proof systems in practice? The first reason is that these are really fundamental topics in theoretical computer science, right? The theorems, amazing theorems, as you very well know from yesterday. However, these theorems, when they were first proposed, these protocols were not very practical. For example, when we think of a problem to be proved, like a computation to be proved, we don't usually think of that computation as an instance of graph-free coloring, right? But at the same time, there is a lot of need for things to be proved in the real world. One such thing is authentication, where you're trying to prove that you are yourself, you have some certain identities. Another application is voting, where voters will prove to the administrator that their vote was done, was encrypted correctly. And finally, it also has application in secure computations, where parties would prove that they execute the actions of the protocol honestly. Okay, so these are just some very simple applications, but they all need the use of proofs. And we want these proofs to be practical. Okay, so what does practicality really mean for these proofs? And so the central primitive that we're going to talk about is something called a zkSNARKS. So I will explain this notion in a moment, but basically you should think of it as a proof systems with some very desirable properties. So a proof system basically consists of a prover who will construct a proof that I know a witness to this NP computation. Am I sharing the slides? Sorry. Okay. Yeah. Let me continue. Proof systems usually consist of a prover and a verifier, right? And here I'm just describing the prover. And so, in fact, for practicality, what we actually want is a proof system that is non-interactive, where the prover will construct a proof without having to interact with the verifier. So let me explain the terminology zkSNARKS. Okay, so zk stands for zero knowledge, which means that proofs do not reveal anything about the witness. Next up, we have succinctness, which means that the size of the proof is actually sublinear in the size of the witness. It means that it's even more communication efficient to send the proof instead of sending the witness in the clear. And then we also want the proof to be non-interactive. As mentioned before, this would be very useful in a setting where the prover and the verifier may not be online at the same time. And finally, these are not just proofs, but they are also proofs of knowledge or arguments of knowledge, where the statement to be proved is not just about right or wrong, it's about whether the prover actually knows the witness to a computation. If the prover doesn't know a witness, then it actually cannot construct the proof. Okay. So next, let's just ask this simple question: how is such a magical primitive even possible? And for instance, we had a homework exercise just yesterday showing that non-interactive zero-knowledge proof is impossible to achieve for non-trivial languages, right? So how do we overcome this impossibility results? So the key the key idea here is that in the proof system we considered yesterday, there was nothing shared between the two parties. But once we allow some kind of sharing, then this becomes possible. So the setting here is that the two parties now shared a common reference strings. There will be a string that's generated by some algorithm and will be given to both parties. Okay. And we also sometimes need to rely on idealized assumptions. And so here, what we are assuming is that the two parties have access to a truly random function, and we call this function a random oracle. So this random oracle is like some external interface to both parties, and both parties can query this random oracle for values. The simulator will now be given extra power by either programming the random oracle or injecting a trapdoor into this common reference strings. And that's how we overcome the impossibility result. Okay. However, this random oracle model is actually not what happens in the real world. In the real world, we don't have a random oracle. And so we actually do a heuristic here, and we replace the random oracle in the real world with some hash function. And we just assume that this hash function is random enough so that we can't tell it from a random oracle. So given this shared resources, the parties can now do a non-interactive zero-knowledge proof. Okay. Finally, if we want to additionally achieve succinctness, which is where the proof size is very small, then we have to make very strong assumptions. In this sense, strong assumptions are actually necessary. And this was a result back in 2011. So I will not talk about details on how these zkSNARKs are constructed, but I would just give you a general framework for how they're built. Okay. So first, you start with an interactive proof, which is often unconditionally sound. You don't need any cryptography for this to be complete and sound. But this is interactive, and the proof size might be very large. And so what we need to add this with some cryptographic compilers. And the result will be a zkSNARK. So these cryptographic compilers, what they do is they either remove interactions or they let you commit to something, such as a polynomial, in a very succinct manner. And then I will tell you the main applications that zkSNARKs has found is that it's in blockchains. So a blockchain is just a block of transactions. Every block consists of several transactions, and they are added on top of each other. It's like an append-only linked list. Okay. Now the transactions on basically all blockchains are public, so we can actually look at them and see what are the transactions. And this leads to very easily identifying users of the blockchains. And they're actually now like a business to identify and de-anonymize blockchain users. So this is undesirable for privacy, right? And the fix for this is to use zkSNARKs. So now we post a proof that a transaction has occurred on the chain instead of posting the transaction themselves. So now we just replace all the transactions with proofs, and that we verify these proofs are correct. These would achieve privacy. In particular, it would hide the identity of the participants. It will also hide the transaction value. And finally, replacing transactions with proofs will also improve scalability, meaning that the blockchain can become more powerful. It can support many transactions than before. And this is because of, first of all, succinctness. It means that proofs will be shorter than transactions. And secondly, the verification will be faster as well. So finally, I will talk about some future directions here. The first open problem is to further improve the efficiency of these proofs. And the efficiency here is mostly on the prover. Proving is still very much slower than computing in the clear. And this efficiency bottleneck actually precludes the applications of zero-knowledge proofs to other domains. Okay, I will also talk about a more theoretical issue, which is something that I'm working on, which is that beyond soundness, what security properties do these non-interactive proofs need to have? So one such property is something called non-malleability. And it's the property that if you're given a proof, you cannot change it into a proof of a related statement. And another property we want to have is security when composed with other protocols. It may be the case that two protocols in isolation are secure, but when you use them together, they're not secure. And so we want to rule out this possibility for these proof systems. And finally, it's also very interesting to consider real-world use cases beyond blockchains. So these are papers that were just from last year. So for example, we could consider ZKPs in private machine learning, where, for example, the model might be private, and then the model will prove to you that it correctly performed an inference. The second application would be to content moderation. So in this example, you would be the prover, and you would post a proof saying that for example, your network transmission follows some policy guidelines. And lastly, we could consider applications to judicial systems as well. And here the contribution is more sort of in a sense, it's less about the efficiency, but just the concept of zero-knowledge proofs in general, which is somehow lacking in the judicial systems. And incorporating this kind of thinking will allow to resolve like a lot of dilemmas in law. Okay. So that is my talk, and thanks for listening.
Thank you so much, Jung. That was also very interesting. Yeah, I would like to thank again all of our speakers. They are all here, so maybe if you all have questions, they're still here and they can answer. I mean, questions from any talk. Yeah, if you don't, in that case, thank you so much again. And I see no questions. Yeah, so see you around.
Bye, friends. See ya.